Well, ExxonMobil is a very large energy company. It operates across the globe. It finds energy, it produces energy, it sells energy. This energy powers homes. This energy powers industries. This energy powers transportation. The company also manufactures chemical products. These products are used in countless, everyday items. This essay will explain how the company works. It is a technical guide for engineering students. We will use real-world cases to explore the system. This system is complex and highly integrated. Understanding it requires a systematic approach. The company is structured along a value chain. This chain has three main parts: upstream, midstream, downstream. Upstream is about finding and extracting crude oil. Upstream is about finding and extracting natural gas. Midstream focuses on transportation. Midstream focuses on storage. Deepwater production is a key part of the upstream sector. It involves extracting oil and gas from beneath the seabed in water depths greater than 400 meters. The Liza field, offshore Guyana, is a prime example. The water here is over 1,800 meters deep. Production is centered around a floating production, storage, and offloading vessel. The Liza Destiny FPSO is a converted oil tanker. It is a massive, complex facility that floats above the oil field. It processes the fluids from the well stores. The processed crude oil offloads it to shuttle tankers. Engineers here face immense technical challenges. The wells are drilled through thousands of meters of water and rock. Subsea trees, complex valve systems are installed on the seabed to control flow. They must operate reliably under immense pressure and at low temperatures. Flexible flow lines and risers connect the wells to the FPSO. These conduits must withstand constant motion from ocean currents and waves. Flow assurance is a major concern for subsea engineers. Midstream is the critical link between upstream production and downstream markets. It encompasses the transportation and storage of crude oil and natural gas. For natural gas, pipelines are efficient over land. However, for transport across oceans, liquefied natural gas is the primary method. The PNG LNG project in Papua New Guinea is an excellent case study. It gathers natural gas from fields in the highlands. It then transports this gas via a 700-kilometer pipeline to an LNG plant near Port Moresby. This plant transforms the gas into a liquid for shipment. The LNG process is a feat of thermodynamics and process engineering. The main goal is to cool natural gas to approximately minus 162 degrees Celsius minus 260 degrees Fahrenheit. At this temperature, the gas becomes a clear, colorless liquid. Its volume shrinks by a factor of 600. This massive volume reduction makes it economical to transport in specialized ships. Before liquefaction, the gas must be purified. Acid gases like downstream operations are where crude oil is transformed into valuable products. This happens at large industrial sites, refineries and chemical plants. The ExxonMobil Baytown complex in Texas is one of the largest integrated sites in the world. It includes a refinery, it includes a chemical plant, it includes an olefins plant. Refineries do not just make one product, they produce a wide range of fuels and feedstocks. The process starts at the crude distillation unit. Here, crude oil is heated and separated into different fractions based on their boiling points, like a complex distillation in a chemistry lab. These fractions are then processed further in various conversion units. For example, a fluid catalytic cracker, FCC unit. The FCC uses a hot fluid-like catalyst to break large, heavy hydrocarbon molecules into smaller, more valuable molecules like gasoline, a hydrocracker unit. It uses hydrogen and a catalyst under high pressure and temperature, often producing high-quality diesel fuel. To meet environmental regulations, hydrotreaters are used to remove sulfur from fuels like diesel and gasoline. Every major facility follows a structured project lifecycle: a deepwater platform, a refinery unit. This lifecycle provides a disciplined path from an idea to a running asset. For engineers, understanding these stages is crucial. The first stage is called identify and assess. Here, a business opportunity is identified, a new oil discovery, or a market need for a new chemical. Engineers perform initial studies to see if it's technically feasible and economically feasible. They assess high-level risks and potential value. The next stage is select, often called FEL 2. In this phase, several different concepts are evaluated. For an offshore field, should it be a fixed platform, or a floating platform, or a subsea tieback? Safety is not just a priority, it is a foundational value in the energy industry. The systems are designed and operated using a concept called layers of protection. The first layer is the Basic Process Control System, BPCS, which keeps variables like pressure and temperature within safe limits. If that fails, an alarm system alerts operators. If the operator cannot correct the issue, a safety instrumented system, SIS, can automatically shut down the equipment. The final layers include physical protection like pressure relief valves. Digital tools and data are transforming how these facilities are managed. A modern plant has tens of thousands of sensors. Those sensors generate a constant stream of data. This data is fed into a central control room where operators monitor the process. Advanced Process Control, APC, uses computer models to continuously adjust the plant's settings. The energy transition is a major focus. The company is investing in low-carbon technologies. One key area is carbon capture and storage, CCS. Diagram: CCS process overview from power plant to underground injection. For engineering students planning a career in the energy sector, building a strong technical foundation is essential. Master the core principles of your discipline. For chemical engineers, this means mass and energy balances, thermodynamics, fluid dynamics, reaction kinetics. For mechanical engineers, it is statics, dynamics, material science, heat transfer. These fundamentals are the building blocks you will use every day. Do not just memorize formulas, strive to understand the physical principles behind them. This deep understanding will allow you to solve novel problems.